Okay, so now there are some results regarding angles outside a circle. Recall how we can have two tangents drawn from the same point. Um, and when that is the case, there's a nice result which says that if I take this arc AD, the bigger one, subtract BC and half it, that's going to give me this angle P. So this is when they are secants. Now if they are tangents, the same property also works, except we have to be careful about the chords or the arc length. So in this case, you take the big arc length and then you subtract the small arc length, half it, and that gives you angle P. In case of a tangent and a secant, then you still have the arc that's outside of the line in some sense and the arc that's inside of the line, and that gives you angle P. Let's look at a case of two circles. Um, when you have two circles, there are three distinct possibilities. They can intersect, um, they can meet on the inside somewhere, and they can meet on the outside. There's a fourth case where they don't meet, but it's not interesting. So there's a result which says for internally or externally tangent circle, that's these cases, a line connecting the center of the line passes through the point of tangency. So this is the center of the bigger circle. This is the center of the smaller circle. Center of the bigger circle, center of the smaller circle, and they pass through the tangent point. And remember, tangent is always 90 degrees with the radius. Okay. Example, determine the length of the stock L, which is required to make this gauge, which is shown below. So this gauge is not semicircular, it's just made up of arcs of various circles as well as straight lines here. To solve this problem, we'll first observe that there is a certain sense of symmetry in this gauge, even if it may not appear so in the way I've drawn it, which means we can focus ourselves on one half of this. Now the property we're going to use is that these circles are internally tangent, which means this is a straight line and there's a 90 degrees here. Now, let's see, look at all the information that we have. Also notice that this dashed line is parallel to L. So if we can find, we know this length is the radius. This is 26.52. So if we can find this missing part, we are done. To do that, we need these two other sides, y, and let's call this z. And then it's a right angle triangle. Observe that z is just the bigger radius, which is 75.30. Subtract a smaller radius, which is 26.52. So that is 75.30 minus 26.52. That is 48.78 millimeters. Now, as far as y goes, the calculation for y can be done this way. We know this is 17.5, all of this is 65, and the radius is 75.30, which means this is 75.30 minus 65, which is 10.30. Then y just becomes 10.30 plus the 17.50. If you look right here, y is just this distance plus the distance between those two lines, which gives me 27.80 millimeter. So my length x is just going to be x squared is going to be z squared minus y squared, which when I plug in, and then I take the square root, so that's going to be 48.78 squared minus 27.80 squared is going to be the square root of that, which comes out to 40, or rather x comes out to 40.08 millimeter. So again, it's a very subtle use of the fact that internally tangent circles are connected by a straight line, and that sort of helps us find this one of the unknown lengths, which is marked by z, and that in turn helps us find x. But we're not yet done, because now what this means is L is the radius of the smaller circle, 5, 2, plus x that we just found, plus another x because it's symmetric, and another of the radius. So adding all of this gives me 26.52 plus 40.08 plus 40.08 plus 26.52 gives me a total of 133.2 millimeters. So that's going to be the length of L that is required. That brings us to end of day 3 videos. The next videos will be on day 4 topics.